Hello and welcome to algebras. In this lecture, lecture number 13, we continue our detour to finite root systems, and today we will talk about the basis of the root system and the Weyl group. Let's start with a reminder what a root system is. Consider an Euclidean vector space E, so a finite dimensional real vector space equipped with an inner product. A subset phi of E is called a root system in E, provided that phi is a finite set which does not contain the zero element of E and which spans E as a vector space. Furthermore, for any element alpha in phi, the only scalar multiples of alpha which belong to phi are plus and minus alpha. For any element alpha of phi, the reflection at alpha, so this is a reflection with respect to the hyperplane orthogonal to alpha, sends phi to phi. And for any two elements alpha and beta in phi, the angle bracket of alpha and beta, defined as a quotient of 2 times the scalar product of alpha and beta divided by the scalar product of beta and beta, this value should be an integer. Elements of root systems are called roots. A root system phi is called irreducible, provided that it is not isomorphic to a non-trivial direct sum of two root systems. A direct sum is when we take a direct sum of two Euclidean spaces and we have a root system in each of them, then their disjoint union becomes a root system in the direct sum. So an irreducible root system is a root system which is not isomorphic to a root system non-trivially constructed in this way. And the aim for the next couple of lectures is to classify all irreducible root systems. So in particular, this will give us a classification of all root systems using the direct sum construction. We start our investigation in the structure of a root system with determining what are possible angles between roots. So let's take two roots alpha and beta in phi. Note that the angle bracket of alpha and beta is not a symmetric thing. However, we can make it symmetric by taking the product of the angle bracket of alpha and beta and the angle bracket of beta and alpha. So this product has a form 4 times the scalar product of alpha and beta times the scalar product of beta and alpha divided by the scalar product of beta and beta times the scalar product of alpha and alpha. So this we can rewrite as 4 times the scalar product of alpha and beta squared, because the scalar product is symmetric, divided by the scalar product of beta and beta and the scalar product of alpha and alpha. And this quantity, the scalar product of alpha and beta squared, divided by the scalar product of beta and beta times the scalar product of alpha and alpha, can be easily recognized as a cosine square of the angle theta between alpha and beta. Now we can note that according to the axioms of the root system, the angle product of alpha and beta must be an integer. At the same time, we know that the cosine has values between -1 and 1, so cosine square takes values between 0 and 1, which means that 4 times cosine square takes values between 0 and 4. In particular, since this 4 cosine square must be a product of two integers, it must itself be an integer, so 4 times cosine square of theta can only have values 0, 1, 2, 3, and 4. And the value 4 corresponds to the cosine being equal to 1, which means that alpha and beta are scalar multiples of each other. In this case, we know that the only possibilities for beta are alpha and minus alpha. So let's consider the remaining cases when the 4 times cosine square of theta takes a value 0, 1, 2, and 3. In this case, we can derive the following consequence, that given two elements alpha and beta in phi, such that alpha is not a scalar multiple of beta, and assuming that the scalar product of beta with itself is greater than or equal to the scalar product of alpha with itself, we get that the only possibilities for theta and the only possibilities for the angle bracket of alpha and beta under these assumptions are the following. So both angle brackets can be 0. This means that the angle theta is pi over 2. And then we cannot say, of course, anything about the ratio of the lengths of the vector beta and alpha, or the squares of the lengths. Theta can be pi over 3, which means that both angle brackets takes values 1, in which case the ratio between the lengths of beta and alpha is 1, so alpha and beta must have the same lengths. Similarly, we can change the sign for the angle brackets, and when both have values -1, the angle theta then will be 2 pi over 3, and both vectors must have the same lengths. The next possibility is when the angle bracket alpha beta is equal to 1, while the angle bracket of beta alpha is equal to 2. Then the value of the 4 cosine square is 2. This means that theta is the angle pi over 4, and the square of the length of beta is twice the square of the length of alpha. If we change the sign, we get a similar situation where the angle theta becomes 3 pi over 4. And finally, in the case where our 4 times cosine takes value 3, we can have that the angle bracket of alpha and beta is 1, then the angle bracket of beta and alpha must be 3, so the angle is pi over 6, and the ratio between square of the lengths is 3. And changing the sign, we get the angle 5 pi over 6. So these are all possibilities. In the previous lecture, we had the following picture, which shows us all possible root systems of rank 2. Now we can explain this picture. It is very easy to see that all these 4 pictures give us root systems, and we see that the angle pi over 2 is realized on this picture of type A1 times A1, on this picture of type B2, and on this picture of type G2. All these 3 pictures have roots which are orthogonal to each other. The angles pi over 3 and 2 pi over 3 are realized here in the root system of type A2 and here in the root system of type G2. The angles pi over 4 and 3 pi over 4 are realized in the root system of type B2. And finally, the angles pi over 6 and 5 pi over 6 are realized here in the root system of type G2. Taking into account that no other angles are possible, it is very easy to see that these are the only possible root systems of rank 2. Next, let us talk about positive and negative roots. For a root alpha, we denote by h sub alpha the hyperplane orthogonal to alpha. That is the set of all elements xi in E such that the scalar product of alpha and xi is equal to 0. Now let us consider the union of all hyperplanes H alpha, where alpha runs through phi. Since each H alpha is a codimension 1 subspace of E, and the field of real numbers is infinite, the union of a finite number of codimension 1 subspaces cannot be equal with the whole space. So this union is different from E. So in particular, the complement of H in E is non-empty, so we can fix some element in this complement. Moreover, we can consider the connected component in this complement, and these connected components are called Weyl chambers. So we fix some element omega in the complement to H in E. For this fixed omega, a root alpha in phi is called positive if the scalar product of alpha and omega is greater than 0. And this root is called negative if the scalar product is less than 0. Note that the scalar product is non-zero because omega is not orthogonal to any root by assumption. So therefore, for any root, the scalar product of this root and omega is non-zero, which means that each root is either positive or negative. So we denote by phi plus the set of all positive roots and by phi minus the set of all negative roots. This gives us a decomposition of phi into a disjoint union of 2 subsets, the set of all positive roots and the set of all negative roots. A priori, this decomposition depends on the choice of omega, but of course it's clear that in reality it depends on the choice of the Weyl chamber rather than omega. If we will vary omega staying inside the same Weyl chamber, then we cannot change the signs of scalar products with any root, because we stay within the connected component when we took away all hyperplanes where some scalar product is 0. Therefore, this decomposition in reality depends only on the choice of a Weyl chamber. So here is an example of the root system of type A2. So we have 6 roots, and two of them are denoted alpha 1 and alpha 2. For each root, we have the corresponding orthogonal hyperplane, which is given here by a dashed line. And let's choose the Weyl chamber, which is shaded on the picture. So in particular, the root alpha 1 plus alpha 2 belongs to this Weyl chamber, so we take this root as an omega. And then we see that the roots which are positive are those roots which have positive scalar product with alpha 1 plus alpha 2. So here is the orthogonal hyperplane to alpha 1 plus alpha 2. Everything what is on the same side with alpha 1 plus alpha 2 with respect to this hyperplane is a positive root. So alpha 1, alpha 2, and alpha 1 plus alpha 2, these are the positive roots. And everything what is on the other side, namely minus alpha 1, minus alpha 2, and minus alpha 1, minus alpha 2, these three roots are the negative roots for our choice of omega or the corresponding shaded Weyl chamber. So the decomposition of the root system into positive and negative roots allows us to speak about the basis of a root system. So let's fix a decomposition phi into positive and negative roots with respect to some choice of omega as above. We will say that a positive root alpha is decomposable if we can write it as a non-trivial linear combination of positive roots with non-negative integer coefficients. And we will say that alpha is indecomposable if it is not decomposable. Let's note that the fact that phi, and hence also phi plus, are finite sets implies that indecomposable positive roots must exist. Indeed, any positive root which minimizes the scalar product with omega must be indecomposable, because any decomposition of it into a linear combination with positive coefficients would imply that for each non-trivial summand, the scalar product should be smaller. So indecomposable roots definitely exist, and by definition, every positive root is a linear combination of indecomposable positive roots with non-negative integer coefficients. So we denote by pi the set of all indecomposable roots of phi plus, and we call pi the basis of phi, corresponding to this decomposition of phi into positive and negative roots. For example, on the previous slide, the basis pi associated to our positive roots consisted of roots alpha 1 and alpha 2. Here is the example. These were the positive roots alpha 1, alpha 2, and alpha 1 plus alpha 2. And the root alpha 1 plus alpha 2 can be written as a non-trivial linear combination 1 times alpha 1 plus 1 times alpha 2 of other positive roots with non-negative integer coefficients. So this root is decomposable, while roots alpha 1 and alpha 2 are indecomposable. So they form our basis phi in this example. Consequence, every root in our root system phi can be written as a linear combination of elements in pi with integer coefficients such that all these coefficients are either non-negative, this is true for positive roots, or all these coefficients are non-positive, this is true for negative roots. This follows from the observation that for any negative root alpha, the root minus alpha is a positive root. In other words, phi minus is equal to minus phi plus. So the main property of the basis of the root system is that each basis of a root system is also a basis of the corresponding vector space E. Recall that the root system spans E and the basis spans the root system. So the basis clearly spans our Euclidean vector space. To prove this proposition, what we really need to prove is that elements of pi are linearly independent. In order to do that, we need one observation. We claim that if we have two different elements alpha and beta in pi, then the scalar product of alpha and beta must be non-positive. Indeed, assume that this is not the case. Assume that we have two elements alpha and beta in pi, such that their scalar product is positive. And assume that the scalar product of beta with itself is greater than or equal to the scalar product of alpha with itself. Consider the rank 2 root system in the span of alpha and beta given by the intersection of our root system phi with this span. In a moment, we will go back to our list of rank 2 root systems to help us with the argument. But of course, if you intersect a root system with any hyperplane of our Euclidean vector space E, and if this intersection spans the hyperplane, this of course must be a root system in that hyperplane. Note also that alpha cannot be equal to minus beta because they both are positive roots. So they are linearly independent, so the intersection of phi with their linear span is definitely spanned by alpha and beta. So this must be a rank 2 root system. And the point is that if we look at our list of rank 2 root systems, we will see that beta minus alpha is a root. So if we assume that the scalar product of alpha and beta is greater than 0, and if the root beta is longer than or the same length as alpha, then beta minus alpha is a root. So if you go to our list of rank 2 root systems, here it is. So if you take this as alpha, so here is a beta, the scalar product is positive, and beta minus alpha is a root. In this root system, so here is alpha, here is beta, beta is longer, the scalar product is positive, beta minus alpha is a root. If this is alpha and this is beta, the scalar product is 0. This is not counted. Here, let's say this is alpha and this is beta. Beta is longer, scalar product is positive, beta minus alpha is a root. This is alpha and this is beta, they have the same length. Scalar product is positive, beta minus alpha is a root. This is beta, this is alpha, the scalar product is 0, so we don't need to count this. And up to symmetry, we now went through all possible cases. So we have proved this observation by looking at all possible rank 2 root systems. If we have two roots which are not scalar multiples of each other, such that the scalar product is positive and such that beta is the same length or longer than alpha, then beta minus alpha is a root. If beta minus alpha is a positive root, then we can write beta as beta minus alpha plus alpha, and this contradicts the fact that beta belongs to pi, so it should be indecomposable. Here it is written as a sum of two positive roots. If alpha minus beta is a positive root, then alpha can be written as alpha minus beta plus beta, which is again a contradiction. Of course, either beta minus alpha or alpha minus beta must be a positive root, so in any case we get into a contradiction, which proves our claim. The scalar product of two elements in pi must be non-positive. Okay, now let us continue with the proof of linear independence. Assume that elements in pi are linearly dependent and write a non-trivial linear combination which is equal to 0. This is a sum over all alpha in pi, alpha with a coefficient r alpha. So some of the coefficients r alpha can be 0, some coefficients will be positive, and some coefficients will be negative. Note that as soon as we have some positive coefficient, we also must have some negative coefficients. Otherwise, the scalar product of this with omega would be strictly positive. Let's leave all summands with positive coefficients on the right side of the equation and move the summands with negative coefficients to the other side. This gives us a vector v, which can be written as a sum over all beta in pi, r beta beta. So here we sum over all beta in pi such that r beta is greater than or equal to 0. And the same vector can be written as a sum over all gamma in pi such that r gamma is less than 0 and then minus r gamma gamma. Using these two expressions for the vector v, we can compute the scalar product of v with itself. So we plug in the first expression for the first occurrence of v in the scalar product, and we plug in the second expression for the second occurrence. This gives us a double sum over all beta and gamma as above, r beta times minus r gamma times the scalar product between beta and gamma. Note that r beta is non-negative, minus r gamma is positive, and the scalar product of beta and gamma is non-positive by the previous claim. Therefore, this sum is non-positive. But this is a scalar product of the vector with itself, and our scalar product is positive definite. This implies that v must be 0. So the only possibility is the scalar product must be 0, which means that v must be 0. And if v is 0, then in this expression, all coefficients r beta must be 0. If any of them is non-zero, the scalar product of this vector with omega is non-zero. So this proves the linear independence of elements in the basis, and hence shows that the basis of a root system is necessarily a basis of our Euclidean space. Now let us talk about the Weyl group. The Weyl group W of our root system phi is defined as a subgroup of the general linear group of our vector space E, which is generated by all reflections as alpha, where alpha is a root. Note that all reflections are orthogonal linear transformations, so W already belongs to the subgroup OE of all orthogonal linear transformations of E. Since our root system phi is finite and generates E, and each S alpha preserves phi, then S alpha must be uniquely defined by what it does to phi, because it's a linear transformation and phi spans E. Therefore, this implies that the group W must be finite, because each element of the group is uniquely determined by what it does to a finite set. Here is a very useful lemma. Let pi be a basis of our root system phi and alpha be a root in pi. Then the corresponding reflection S sub alpha permutes all positive roots different from alpha. Clearly, by definition, S alpha sends alpha to minus alpha, so the root alpha is sent to a negative root. The claim of this lemma is that all other positive roots are sent to positive roots by such as alpha. Proof: let's take some positive root beta different from alpha. Then beta must have a positive coefficient at some root gamma in pi different from alpha. And our linear operator S alpha does not change the coefficient at gamma, because S alpha of beta is beta minus a scalar multiple of alpha. The coefficient in gamma remains the same. Here it is important that pi is a basis of our vector space E, so expression of a root as a linear combination of elements of the basis is unique. So in particular, it follows that the coefficient at gamma remains positive. Therefore, the corresponding root must be positive. Positive roots are the roots which have non-negative coefficients with respect to the basis, and negative roots are roots which have non-positive coefficients. So if S alpha of beta has a positive coefficient to one element in the basis, it must be a positive root. Denote by W0 the subgroup of W which is generated by all reflections with respect to roots alpha in our chosen basis. Such reflections are called simple reflections. So the difference here is that the group W is generated by reflections with respect to all roots, while W0 is generated by reflections only with respect to the roots in the basis. By definition, W0 is just a subgroup of W. However, shortly we will prove that W and W0 coincide. In order to prove this, we start with considering the W orbits of the elements of our basis. So here the claim is that for any root beta in phi, there is a root alpha in our basis pi and an element W in the group W0 such that beta is equal to W of alpha. Proof: without loss of generality, we may assume that beta is a positive root outside of our basis pi. Indeed, if we can prove this claim for all positive roots, then the symmetric claim for negative roots would be that any negative root is in the W0 orbit of minus pi, but since each alpha in pi can be swapped to minus alpha by the corresponding S alpha, then we will get that each negative root is also in the W0 orbit of pi. So we assume that beta is a positive root outside pi. Assume first that the scalar product of beta with any root in our basis pi is non-positive. Then we can write beta as a linear combination of roots in our basis with non-negative integer coefficients r sub alpha, and plugging in this expression into the second variable, we can compute the scalar product of beta with itself as a sum over all alpha r alpha and then the scalar product of beta with alpha, and using the assumption that the scalar product of beta and alpha is non-positive, we get that the scalar product of beta with itself is non-positive. But then it must be 0, which means that beta must be 0, and this of course contradicts the fact that phi doesn't have 0 vectors. Consequence: there is at least one root alpha in our basis pi for which the scalar product of beta with alpha is strictly positive. So we choose such alpha in pi such that the scalar product of beta and alpha is positive. And then let's look at the image of beta under the reflection as alpha. Since beta is not in pi, this reflection stays positive, so this is a positive root. And let's compute the scalar product of this positive root with our vector omega, which defines phi plus. The scalar product of S alpha of beta with omega is equal to, so S alpha of beta is equal to beta minus scalar multiple of alpha. So we write this expression and we get the scalar product of beta with omega minus the scalar product of alpha with omega. This is a positive real number because of our definition of positive roots. 2 times scalar product of alpha and beta, this is positive by our assumption, divided by scalar product of alpha and alpha, which is also positive. So this second summand is strictly positive. So we deduce that the scalar product of S alpha of beta with omega is strictly smaller than the scalar product of beta with omega. So we can now complete our proof by induction on the value of the scalar product of our root with omega. We have only a finite number of such values, and all these values are linearly ordered because they are positive real numbers. So we can do the induction on these values. And we know that if the value is minimal, that such element is necessarily in the basis for which the statement is clear. One consequence of this theorem is, as advertised before, that W is equal to W0. In other words, W is generated by reflections with respect to roots in our basis. Indeed, we have just shown that any root is W0 conjugate to a root in the basis. Therefore, any reflection with respect to any root is also W0 conjugate of a reflection with respect to a root in the basis, that is, to a simple reflection, which means exactly that the group generated by all simple reflections is the whole W. Our next question is to determine which elements of W stabilize the set of all positive roots. The claim is that there is only one such element, namely the identity. To prove the claim, we need to show that each non-identity element sends some positive root to some negative root. So let's take a non-identity element and write it as a product of simple reflections in the shortest possible way. This is possible because of the previous slide. Any element of W is a product of simple reflections. So let's write it in the shortest possible way, but still K is a positive integer. We are going to prove that such element W sends exactly K positive roots to negative roots, and so it cannot preserve the positive roots. And we prove this by induction on K. The case K is equal to 1 corresponds to the case where W is a simple reflection, and in this case we know that it sends the corresponding simple root to its negative and permutes all other positive roots. So the basis of the induction is clear. We have to prove the induction step. Consider the element W prime, which is just the element W with S alpha 1 removed. So by the inductive assumption, this element can now be written as a product of K minus 1 simple reflections, and this is the shortest possible way to write it. So by the inductive assumption, this element sends exactly K minus 1 positive roots to negative roots. Assume towards the contradiction that S alpha 1 doesn't add up one more positive root, sending it to the negative. So what it has to do, it must send one of these K minus 1 negative roots back to a positive root. And of course, the simple reflection S alpha 1 certainly can only send the negative root minus alpha 1 to a positive root. So now we write the element W in the following way. S alpha 1, this is our first element, and in the element W prime, we pinpoint the simple reflection S alpha I inside, which sends, of course, root alpha I to the negative root minus alpha I, and this negative root minus alpha I is exactly the preimage under the element A, which is between S alpha 1 and S alpha I, of the root minus alpha I. So we can write W in this form. But then in this situation, we of course have that the simple reflection with respect to alpha 1 is the conjugate of the simple reflection with respect to alpha I under the element A. But in this case, we then can write W as a product of, so we rewrite S alpha 1 as A as alpha I, A inverse, and then we write W prime. And here we see that A prime and A cancel, S alpha I and S alpha I cancel, and what remains is A times B, but this element requires exactly K minus 2 simple reflections, which contradicts to the fact that we assume that W can only be written as a product of K simple reflections. So this contradiction completes our induction and hence establishes the fact that the only element of W which sends positive roots to positive roots is the identity element. Now let us derive some consequences of this fact. The main consequence is that the group W acts simply transitively, which means it acts transitively and with trivial stabilizer on the set of all Weyl chambers. Indeed, since Weyl chambers are in bijection with positive roots, we already know that W acts without stabilizer on the set of Weyl chambers, so we only are left to prove the transitivity of the section. So denote by H prime the union of intersections of different hyperplanes H alpha and H beta. Note that each such intersection is a codimension 2 subspace of E. So, and the union of a finite number of codimension 2 subspaces must be path connected. So in particular, if we have two Weyl chambers X and Y, we can fix a path from a point in X to a point in Y, which avoids H prime. Now we can follow this path starting from a point in X, and we follow this path, and every time we cross some H beta, and since we avoid H prime, we cross a unique H beta. We cannot cross two or more H betas at the same time. Anytime we cross H beta, we apply the element S beta and go from one Weyl chamber to another Weyl chamber. Going along this path, we produce an element of W which maps our Weyl chamber X to the Weyl chamber Y. So this completes the proof of our statement that W acts simply transitively on the set of all Weyl chambers. But this also implies that W acts simply transitively on the set of all bases in phi. Indeed, as we have already noticed before, Weyl chambers are in bijection with all bases in phi. Therefore, this statement follows from the previous statement directly by construction of the basis. Thank you very much. Hope you enjoyed the lecture.